in the universe, and hopefully someday have an answer to one of the greatest mysteries that humanity has ever encountered, really, which is whether or not we're alone in the universe and whether or not there's life off of Earth. To introduce myself, my name is Sarah Al-Ahmed. I am the host and producer of Planetary Radio. Planetary Radio is a weekly show. It comes out every Wednesday. It's been going on for over 20 years. And we invite scientists and other people who are involved in space science, whether through art or through communication, to share all the discoveries that are going on as we're exploring our solar system. If things are really, really big, some big announcement that's outside of our solar system, sometimes we cover that as well, because the discoveries that are going on these days are just immense and almost bombarding. There's so much going on in space science, especially as we ramp up toward new missions coming up. The Planetary Society is the organization I come from. We're the world's largest and most influential space advocacy organization. We have members all around the world, and together we not only band together to try to teach other people about science, but we have a few specific goals, which I'll get to in a moment. You may recognize this guy in the middle, Carl Sagan. These are our three founders, and they created the Planetary Society to try to prove, specifically to the US government, but also to other governments around the world, that everyday people really cared about space exploration. It was in a time post Apollo where they were kind of ramping down in all the funding for NASA space science. And in order to make sure that we kept on in this journey to try to explore the worlds beyond, they needed to prove to people that there was enough interest. And so the Planetary Society was born. Today, we're led by Bill Nye the Science Guy. He's our CEO. This is a picture of me and my brother with Bill Nye at the most recent eclipse. I don't know if you guys got to see that total solar eclipse, but if you ever get a chance to see one in your lifetime, please do. They're amazing. So, what the Planetary Society does is we
Oh, I'm
explore.
I'm sorry, Sarah. May I just interrupt to say
Yeah.
I met my brother's family. We actually arranged our trip before I knew about the Planetary Society one. So
Mhm.
we were in Temple, Texas, and the eclipse was fabulous. Anyway, please go
All
on.
right. No, it was amazing. We actually threw a festival with over 800 people. Many flew out from all over the world to come to this festival together, and we were very lucky the weather let us see it. There was a small gap in the clouds right around the eclipse that, it was very tense, but we actually got to see it. It was amazing. But so together, we're trying to explore worlds and make sure that the missions that do that have enough funding to go forward. We're also trying to defend Earth, specifically from asteroids, but also from comets and other things that could impact our planet. Honestly, the dinosaurs didn't have a space program, and if they did, maybe life on Earth would have gone differently. We're trying to make sure that we can protect our planet now that we have the technology to do so. It needs a lot more funding, and we're right on the cusp of a whole new age of this. That is not what this talk is about, but feel safe because I think we're about maybe 10, 15 years out from having most of the most dangerous of these objects classified and under our understanding. And finding life. This is our last main goal, and it is one of the most challenging things I think humanity has ever tried to tackle. And we'll get into this a little bit today, specifically in the realm of habitable worlds. I called this talk Beyond the Pale Blue Dot in reference to this image. It's called the Pale Blue Dot image, and it was taken by the Voyager 1 spacecraft in 1990. So the Voyager spacecrafts are the only spacecrafts that humanity's ever created that have exited our solar system. So they've gone beyond Neptune, beyond Pluto. They're out into the Kuiper Belt, and they're out traveling into interstellar space. And at a point about 4 billion miles away from its launch point from Earth, Voyager turned back around, pointed its telescope back at Earth, and got this image. And if you look right there, that little dot in the middle of that sunbeam right there, that is our planet Earth. So, as Carl Sagan famously said, that is the only home we've ever known. Everything we know about life exists on that world. And it is very important, not just that we protect this world, but that we try to find other worlds like it beyond us. Because I don't know about you, I think life in the universe is one of the most mysterious and beautiful things we could possibly pursue knowing more about. But it is challenging. So, what we have to do is start with what we know about our own planet. So this is an image, another Earthrise. You may remember the very famous Apollo Earthrise, but this is a new one from 2015 from the Lunar Reconnaissance Orbiter. It's a mission that's been orbiting the moon for quite some time. And what we know about life on Earth is that it needs three things in particular. We need water, specifically liquid water, in order to facilitate chemical reactions. We need energy, which can be in many forms, sunlight, but also hydrothermal energy and geothermal energy, that kind of thing. And then you need the right mix of chemicals. Specifically, you need carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So these are like the main chemicals that we look for when we're looking for the potential for life off of Earth. And of course, it does help if you have a stable climate and if you have an atmosphere. But those two things, having an atmosphere might not necessarily be the only way that life exists. We've only found life on Earth, but there are many other ways that life could exist. So we'll use this as an example and look for that. But as we get to know more about worlds outside of our solar system, it might get more complex and we might have a more complicated understanding of what life is eventually. Now, there are actually some worlds in our solar system that could potentially be habitable for life. The one that everyone thinks of first off is Mars. Now, we don't think that this is habitable in modern day, although there are some methane signatures that we have detected on Mars that are a little mysterious. We're still investigating, but we're specifically curious about whether or not Mars had life in the past. It used to have oceans of liquid water, and we know that there is water still underneath the surface. That was a discovery they just announced recently. It was either last week or the week before. So we know that water still exists there. And there's some water ices at the pole, along with carbon dioxide ice. The thing that we're trying to do to really figure out whether or not life exists on this world, among many of the other missions, there's an entire fleet of missions out there, including this one that took this image. This is the Hope orbiter from the United Arab Emirates. But we have this rover called Perseverance. Perseverance has been in a crater called Jezero crater on Mars, taking samples. And this area is really interesting because we know in the past it used to be a river delta. So there was water pouring into this crater, and we can see the sediment deposits. So we sent this rover there, and it's been taking sample cores, it's caching them to hopefully return to Earth. This one recently was so exciting. I took a selfie with the rock that it cored. You can kind of see right below it, there's this kind of little black dot on this rock down there. This is the Chava Falls sample. They've detected potential biosignatures in this. There's some indication that there are some chemicals and other things in the rocks that could be from previous tiny, tiny microscopic life. We're not sure yet. We want to bring the samples home, but once we can start analyzing these things, we can get a better idea. And that'll give us more of an understanding of whether or not worlds like this could potentially be habitable. Now, the two that I'm really excited about are also in our solar system, but they're actually icy moons. So if you look at some of the images that the James Webb Space Telescope has taken, we've got our outer body solar system planets, gas giants and ice giants, Jupiter, Saturn, Uranus, and Neptune. Now, there are some moons that could have potential liquid water oceans around Neptune and beyond, but the two I'm going to look at specifically are around Jupiter and Saturn. This is a picture of Europa in front of Jupiter. Europa is one of the four Galilean moons. It's one of the four big moons. If you ever point a telescope at Jupiter, you'll be able to see it. But Europa is fascinating. This is an image of it from the Juno orbiter, which is still going around Jupiter right now. It's kind of spiraling in toward the planet, and recently got some really crazy images of Io, which is the most volcanic world in our solar system. But Europa has this outer icy crust, and underneath that crust is more water than we have on our planet several times over. There is a lot of water underneath there. We're not sure what's going underneath this icy crust, whether or not there is a potential for life, whether or not the circumstances could be okay for it. But this is one of the main targets in our exploration. There's a lot of things that are really mysterious about this moon, including you'll see these kind of striations on the surface, these kinds of cracks and the colors underneath. We're not really sure what creates this cracking system on this moon. So there's a lot of mysteries left to be solved. And later this year, we're going to be sending the Europa Clipper mission out to go investigate this world, which is something we've been advocating for a long time. It's launching in October, and I'm really hoping some of the people on our team can go see this launch because if this thing gets the data that we want, this could potentially revolutionize our understanding of this moon and the search for life in our solar system. I did hear recently that there are some issues with some of the transistors on it, so it might get paused for a little bit. We'll see. But fingers crossed for Europa Clipper. And then out to Saturn. This is an image of Saturn from Cassini. You can see two of its moons, Mimas and Tethys, and also the shadow of the rings on this planet. The Cassini mission has already ended. It plunged into Saturn and burnt up. But part of why it did that was because as it was exploring the moons around Saturn, specifically one called Enceladus, it realized that moon it could potentially be habitable. It is one of the greatest targets for it. And in order to make sure that this orbiter didn't accidentally crash into it and potentially contaminate it, they decided to burn the Cassini spacecraft up in the atmosphere. Now, if you take a look at this image, which is also from Cassini, this is a backlit Saturn. The sun is on the opposite side, so we're kind of getting this eclipse, which really brings out the ring system. And if you look at right here, there's this outer ring we call the E ring. Now, the E ring is made mostly of water ice, and that water ice comes from Enceladus, this moon of Saturn. And just like Europa, it has this outer icy crust, and underneath there's a bunch of liquid water. But unlike Europa, we've actually been able to test some of the water out of this moon because Cassini got close enough to fly through the jets of water that are spewing out through the cracks in this moon. And what it found was that there are organic compounds, definitely liquid water in there. There's evidence of hydrothermal vents, which we think might be a very good place on Earth for the formation of life. We also found phosphorus, which is one of those chemicals we were looking for life on Earth. You may remember from high school, the mitochondria in your body are the powerhouse of the cell. That's because they produce ATP, and that P, adenosine
Hello.
triphosphate, is phosphorus, right? So that
Oh,
chemical
yeah.
is really important for the facilitation of energy transport in the body, and that could indicate that potentially this is another good place for life. I think we're planning some other missions to go back here and reinvestigate in the future, but it will be a while before we get the Enceladus Life Finder. So we'll start with Europa and then move outward. But what about the worlds beyond our solar system? We've looked at some of the places in our solar system that could be good places for life. We can use those as analogs to then look for other habitable worlds, but we're specifically trying to find ones that are like life because, or the ones that are like Earth because we know that life exists here. But that is a very unique challenge. So to start out, we got to figure out how do we actually find other worlds, right? So the easiest way to find other worlds going around other stars is this transit photometry method. And this is actually how I started out doing planet hunting when I was in college. What you do is you point a telescope at a star and you wait for the planet to pass in front of that star. And when that happens, you kind of get this little eclipse. So the star essentially looks like it's kind of fading in brightness. And this brightness dip could indicate that a planet is passing in front of the star. It could be other things like a comet or other things. So you want to make sure that you do enough observations to see it pass more than once and kind of characterize it. But this is the easiest way. There are a lot of other ways we could do it. The radial velocity method, basically you wait for a planet to orbit a star and its gravity will kind of pull that star a little bit as the planet is orbiting. And that creates a kind of Doppler shift in the light, which means it will kind of go a little bit redder over time and a little bit bluer over time. And that cycle back and forth could tell you that there's a planet there. And we can actually use that to kind of estimate how big the planet is, how much gravity it has, and how long it takes to go around, because you can tell that by the light cycles. The ultimate dream of finding planets is this direct imaging method. But trying to spot these tiny planets next to these really bright stars is really challenging. We have done it in the past, and we're going to be getting better at it. I'll tell you a little bit more about a telescope we have upcoming in the future in a bit. But the direct imaging method is it's exceptionally challenging. Um, Here's an example of a direct image. Although you cannot see the planets directly in this image, this is TW Hydrae. It was taken by the Atacama Large Millimeter Array down in Chile. And this here, you can kind of see, this is like a planetary disk. And all these gaps in the disk are actually planets forming. They're scooping up the material in the disk around the star and clustering it and forming new planets. So these are actually baby planets being born. In this image, though, this star system isn't necessarily too bright for us to see it because we're looking in this specific range of light. But the easiest way to actually spot these things going around stars is by using something called a coronagraph. So you can see here, This is an image taken by the Hubble Space Telescope, which is one of our favorite space telescopes, still out there operating over 20 years. But you can see they've blocked out the central star in this image, which allows you to kind of see around it. So in this system, there is a planet that they've actually detected going around here, but they could only see it because they blocked out the light of that star. But as I said, the easiest way to detect these things is actually by watching the planets go in front of their stars and seeing that light dip, that transit method. But there are a lot of other ways that we could do it that I haven't mentioned. Now, two telescopes were really profound in our impact on finding worlds outside of our solar system, and they specifically use this transit photometry method. The first one was the Kepler Space Telescope, and this was a tribute art that NASA created for it when the telescope stopped working or when they shut it down. I lovingly say that Kepler is the telescope that took my job. We used to do this one planet, one star at a time with telescopes, but then Kepler went up there, scanned the sky one section at a time, and took so much data that the field of exoplanet detection became not so much about finding worlds one at a time, but more so combing through the data provided by this telescope. And ultimately, this telescope confirmed over 2,000 exoplanets. Shortly after this one went up, we got the TESS telescope, the Transiting Exoplanet Survey Satellite. And this one scanned the whole sky. If you get a chance to watch the videos of how this thing worked, it was really cool. It went chunk, 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 chunk all the way around and then did the under sky and then dumped all of that data onto the internet. And since this telescope went out there and started doing that, we have found thousands and thousands of more planets, but we're still combing through the data. There are thousands left to be confirmed and to be detected in all of this data. And if you want, there are citizen science projects online through programs like Zooniverse and things like that that will allow you to help comb through this data because there's simply too much of it for anyone to get through by themselves. And helping to do this kind of detection manually actually helps us train AI systems and other models that can then be better at detecting these things in the data by themselves. Now I checked it this morning so I could let you guys know. So far, we have 5,747 exoplanets, planets outside of our solar system that we have confirmed. But there is a lot more. You can see there's like 7,208 test project candidates. So those are still being reviewed. Only 545 of the test ones have been confirmed at this point because you need follow-up observations to seeing them passing in front of their stars again. But that is a wild start. Like it was only maybe not even 30 years ago we found our first exoplanets, and now we're up to the point where we have got so many that we can barely analyze all of them, and it's literally just the beginning. And then something spectacular happened. The James Webb Space Telescope, which took over 20 years from its ideation to its production, got launched into space. And this thing has completely changed, not just the way that we kind of study exoplanets, but also our understanding of the broader universe. One of its first images that came out, this is one of my very favorites, so I always like to show it. This is an image of the Carina Nebula from JWST. Nebulae are basically these kinds of remnants of stars where all this material gets sloughed out into space or just gas clouds that come together. There are a few different kinds of nebulae, but when all the gas and dust comes together, it forms these stellar nurseries where new baby stars are being born. So all these little sparkly stars down in here are all being formed from this gas and dust, except for the ones that are super far away in this image. But what's cool about this telescope is that it's not just amazingly spectacular at taking images of space, but it can also use this transit method to do something that we weren't really capable of doing before. You can see here when the planet passes in front of the star, here this little outer rim shows us the atmosphere of the world. If you can study the spectral signature, essentially, you look at the light coming off of the star in different wavelengths, that can tell you what the star is made of. And if you can compare that to what it looks like, what that spectrum looks like when the planet passes in front of the star, you can learn more about the star or the planet's atmosphere. So we can use this method to actually tell us what is in the atmosphere of these worlds. And this is one of the first times we've had a tool powerful enough to let us do this for many, many worlds. And we're finding some wild stuff. As an example, this is one of my favorites. This is a world called K2-18b. This is just a concept image, obviously, but when we looked at the atmosphere on this thing, we found some really cool stuff. First off, methane. Methane is a pretty good indicator of life. We also found carbon dioxide. But one of the things I think is really cool about this, although it has to still be confirmed, they found this chemical called dimethyl sulfide, which on Earth is mostly only produced by living creatures in the ocean, certain planktons and stuff. We haven't found that on other worlds outside of our solar system before. This is one of the first times we've detected something like this. And although we still have to confirm this, that is a fantastic indication of the power of this instrument. We've never been able to do this kind of science before. And this is just a start. Now that we've done this with JWST, we have an understanding of how to create telescopes that can fold up to the size and put them inside of a rocket and launch them because generally our rockets are pretty limited in their size. In order to get something like a telescope of that size up there, you got to fold it up all origami style and then unfold it, which is why everyone was so scared it wasn't going to work. But now that we've mastered that, people are trying to advocate for this next generation telescope, this habitable worlds observatory. Now, this one, they're going to combine the technology of JWST with an even better coronagraph, the thing that blocks out the light of the star, to directly image other worlds going around other star systems and hopefully find worlds like Earth. And the real challenge here is that bigger planets are basically easier to find. They can reflect more light, they can block more light, but finding something the size of Earth, that's really difficult. We've found some so far, but we really need better instruments in order to broaden the search and give us a real grasp on how many are out there. Here's an example of what happens when we apply a coronagraph to our sun. You could see by blocking out the sun, you could see the streamers coming off of the sun and the sun's corona. That's part of its atmosphere, which we saw very clearly during the total solar eclipse. That's part of why eclipses are so special. It's kind of like having a coronagraph in the sky all by itself, but it's the moon. And you can see in this image, by blocking out the sun, we've managed to bring Mars out in this image, whereas you probably wouldn't be able to see that if you're just taking an image of the sun directly. So, using these methods, what are the most Earth-like worlds we have found so far? This is one, Kepler 18 or 186f. This was the first one, the first validated Earth-sized planet orbiting a distant star in the habitable zone. The habitable zone is a space just the right distance away from a star that liquid water could exist on the surface. And of course, this changes depending on what size star, how bright it is, that kind of thing. So the habitable zone is in a different location for each star. Note too that this is only for liquid water on the surface of a world. If we have worlds that have icy surfaces like Europa and Enceladus, like I pointed out earlier, there could still be liquid water under the surface further out from the star. So that's going to be a little more tricky to find, but we're trying to find worlds like this that could potentially have liquid water on their surfaces. Then there's Kepler 482b. This is the closest analog that we've ever found to our planet and sun so far, but this one is about 60% bigger than the Earth. Note there that it's bigger because bigger ones are easier to find, right? If we want to find ones that are even smaller, we're going to have to create better technologies and better ways of finding these. But this is my favorite star system outside of Earth, the TRAPPIST-1 system. Part of why I love this system so much is because it doesn't just have one potentially habitable world, it has a bunch of them. So if you look at this, at the TRAPPIST-1 system, if we were actually looking at in a scale size to our solar system, could fit inside the orbit of Mercury, right? These worlds are really, really close to their star, and their star is much smaller than our sun. So it's cooler, but it's also a type of star. These red dwarf stars tend to be more active. They tend to put out more solar flares and other things that could potentially impact these worlds. So we're still not yet sure how habitable worlds around this type of star could be, given just how feisty they tend to be. But in this image, we've marked out the habitable zone around the star using colors. So the green area is where the habitable zone is around TRAPPIST-1. And if you look at this, this looks like potentially three of the worlds in this system are in a space where they could have liquid water on the surface. But now using JWST, we are just in this year beginning to point that telescope at these worlds and begin to analyze whether or not they have atmospheres. So we're just at the beginning of doing the science. And in the next coming months, I anticipate we're going to get some really interesting results about these worlds. Totally unrelated to life, but I do want to point out that because all of these worlds are so close together and so close to their star, they actually orbit in resonances. Their gravity impacts one another. So every time one of them goes around, another one goes around a certain number of times, and the other one goes around a certain number of times. It's a very musical kind of system because they all go in these systems relative to each other in their orbits. It's absolutely wild. And if you were living on one of these planets, you could look up in the sky and see multiple worlds up there in the sky, much more vibrant than we have in our solar system because they're all so close together. So if there are creatures living on these worlds, I bet they have really beautiful night skies, unless they're too close to the star and they're tidally locked. Totally different story. So these are the worlds in the TRAPPIST system. Oh, I feel like my last slides have disappeared, so I guess I'll leave it there. But these are the beginnings of this journey toward understanding more habitable worlds. We're just maybe 20 years off from having a telescope that can actually study these things up close. We're hoping the Habitable Worlds Observatory will be able to identify about maybe 20 to 25 of these worlds and study them. We're gathering all the data using JWST and all of the other large scale surveys that we've done to identify targets for these. And I think that potentially in the next coming decades, we're going to be able to find worlds like Earth and definitively say whether or not they have liquid water on their surfaces and whether or not their atmospheres are like ours. Now, finding intelligent life, that's a total other story. That's a dive into technosignatures and analysis of the waves that come off of these worlds. We're doing those searches as well. But in the meantime, it's far more likely that we're going to find a world with unintelligent life, maybe in our own solar system and maybe beyond. So if you guys have any questions, I will leave it there.
Well, the last thing you said, Sarah, reminded me of the whole debate that finding intelligent life depends on time
Hmm.
because time is so huge in the cosmos more than it is with us.
Yeah.
So will our civilization, will there be any remnant of it on Earth in a million years? I mean, who knows? So it's mind-blowing to actually try to factor that in also.
Yeah, there's a really famous equation called the Drake equation that tries to like put parameters on this, right? And one of the biggest mysteries in this equation, one of the biggest factors that we don't know is how long civilizations like ours last, right? Because say humanity lived for 1 million years, that's still not a long time in the scale of the universe, right? And that we've only been beaming out signals for so long. So even if we did find other creatures, even if we did find their signals, who's to say they were still there? And then communicating back and forth with them would take quite a while if we could even understand them.
Oh, so bringing you back when you were talking about the blue dot, I was remembering that Carl Sagan had to do a lot of heavy lifting to persuade NASA to turn the craft around.
He did actually. I mean, they figured it would be a waste. I mean, you saw the image, right? It's just like one little dot and a bunch of sunbeams. Like, how could anyone possibly like this when they had just seen all these other amazing images coming out of Voyager? He really had to advocate for that because they were going to have to pivot the whole spaceship to do it. But it became one of the most iconic images in the history of space exploration. And I still get really emotional thinking about it. He wrote a whole book called The Pale Blue Dot, but there's a really famous speech he gave about it, talking about just the history of the earth and everything that's ever happened here and this idea that you can't see the borders from outer space. We're all just citizens of earth, and every person who's ever started a war over this minute little area on this tiny speck in space. It's a really beautiful concept, and as he said, it underscores our responsibility to preserve and cherish the pale blue dot. It's the only planet we know that's like this. Imagine if it was one of the only planets in the entire universe that was good for life. I mean, that's statistically unlikely, but also given our search and how little worlds we found like ours, it's one more reason why our planet is so precious.
Well, thanks for titling your talk that way to get us thinking about it.
I cry every time I listen to him give his speech. So I really encourage you guys, if you haven't seen his Cosmos show or you haven't heard that Pale Blue Dot speech, get some tissues ready because like I cry every single time.
Oh, do you have a link to that by any chance?
I
Maybe later
do.
send that or put it in the chat. So
Yeah, I can find that.
yeah, because what we do is send around the chat to the folks after the meeting. Um, while we're waiting to see if other Pi members have questions, I think the thing I wanted to ask was, is habitable zone still even a thing
Mm.
since we know about subsurface oceans as harbingers of life?
Right? It does introduce some complexity there. Like there's still some value in defining the habitable zone, just so that we can talk about liquid water on surfaces of worlds. But calling it habitable zone kind of takes on an interesting connotation now that we understand that there are other worlds that can exist beyond that, right? Like we even know that there's a potential for Pluto to have a subsurface ocean, despite being way out there. Not that we think there's life on Pluto, but who knows, right? There's no way we'd know at this point. But I don't know if there's any debate over whether or not we should rename the habitable zone at this point. It's kind of like a
Well,
legacy term.
well, the reason I ask is it sounds like it's our own limitation in looking at it.
Yeah.
And it reminds me of the days when we were trying to, it's like it's something we can measure, so we're overvaluing it. Do you know what I
Hmm.
mean?
No, we're super human centric in almost everything that we do in the search for life. I mean, it's you work with what you know, right? But we really do. We for most of our search have really kind of corralled it around this idea. Like you even see it in the search for extraterrestrial intelligence, the SETI program. They're working primarily with radio waves under this assumption that other species would communicate through space the way that humans did back when the program was formed, which is through radio waves. There are other reasons they might do this because of the frequencies that are most popular on the sky, but they might be kind of dodging the most active ranges of light in the sky so that they can beam signals in a wavelength that isn't commonly produced by stars, as an example. But I mean, who knows? Maybe they communicate in gravity waves. Maybe most life in the universe lives under these icy shells. And how would they even know that there was a broader universe beyond their icy shell, given that their whole existence was underneath the ice? Like, there's so much there to try to figure out. Also, I found a YouTube video that we produced of Carl Sagan's Pale Blue Dot speech, so I'll put that in the chat. Um,
Yeah, and after you do that, I think Tim has a question he put in the chat. So Tim, why don't you ask Sarah?
Thank you. Which one? I put three.
oh,
Has there been analysis of the water vapor erupting from the icy moons to find chemical signatures of life, or at least the rings of Saturn to find chemical signatures?
yeah. The tricky bit here is that when they created the spacecraft, they had no idea that they were going to have to do this kind of science, right? So they did have a thing on board that was capable of testing these chemicals, but it's not capable of telling us whether or not they were specifically derived from life, right? Because the chemicals created, these organic compounds created by life, are really, really complex. But what we did find was that there are these organic compounds. They are complex organic compounds, but we can't say definitively whether or not they were produced by life, right? So we would need follow-up missions there to be able to analyze them more thoroughly. There's also the more complex question of like, how would we even know that those chemicals were associated with life unless we found something akin to RNA or DNA directly in it, right? Um, honestly, I think we'd have to do that kind of science in a lab, probably. But what we did find there was enough of an indication that there's a good chance, which is, we can't say for sure. I'm not saying there's like shrimp in your in Enceladus, but maybe. And we were only able to do it for Enceladus, but Europa. Observations of Europa using Hubble have also indicated that there could be some plume activity. So when the Europa Clipper mission gets there, we might be able to detect whether or not there's plumes there. Um, I don't believe that spacecraft has the ability to test. Like I don't think it's going to be flying through the plumes. But yeah, I mean, it's complicated, right? Like even in the case of Mars, this is why we're trying to get those samples back from the surface of Mars. We've sent way more scientific instruments to that planet than we've sent out to the other icy moons. And even with all of that, you know, the Viking lander did try to do a direct test for life and did find some interesting stuff there. But there was a lot about the Martian regolith we didn't understand. They found perchlorates and other things that are toxic to life as we know it. So we need to get those samples back to Earth and actually test them in the labs because the size of the instruments we would need to really do that kind of detection kind of don't fit, you know, wrapped up into a small little casing in a you know, little rover, unfortunately.
So would SpaceX be able to expedite the Mars sample return?
Potentially. So the there's a couple things going on here, right? This mission continues to be more and more complicated, more and more expensive to produce. And while it is something that is highly prioritized in what we call the Planetary Science Decadal Survey, every 10 years, the scientific community or the planetary science community comes together and creates this list of priorities that they then give to governments to hopefully, specifically to the US government, to hope that this will like change the way that they fund programs. The Mars Sample Return Program does have a majority of the funding, but in order to get it all the way over the finish line, we're going to need additional funding to make sure this mission actually works. And in order to get it all the way there and back again, we're working with the European Space Agency to have like one group work on the lander part for returning things, and the other group working on this like there's the orbiter, the lander, and then the system that jets off essentially. Um, where SpaceX can come in is that launching all this stuff to Mars takes a lot longer depending on how much thrust you get off the ground, essentially. And SpaceX is working on their Starship, which is just that really, really huge one. And they've finally done some tests that are actually working. It hasn't exploded, which is great. It's the largest rocket humanity's ever tried to build. So, you know, whenever it explodes, like please give them a little grace there because you know this is hard. But this is going to give us the capability to launch a lot more objects to Mars and a lot faster potentially. Um, so hopefully, I know we're going to start using this as we're going to the moon with the Artemis program. We're returning humans to the moon, and then we're going to be using it potentially to go out to Mars. I don't know. The real thing that's going to speed this process up is making sure that the program has the funding that it needs, which is why we work so heavily in space advocacy. And every year we do this giant advocacy event where we all go to Washington, D.C. Well, not all of us, but some of our United States members, we go to the Capitol directly and advocate for these missions. So I actually got to do that this year, go to Washington, D.C. and knock on a bunch of people's doors, speak to Congress people and advocate for our sample return. Because, I mean, come on, we didn't even have the Cheova Falls sample at the time. Now that they've announced that we have this sample that has this like really interesting evidence of potential biosignatures, we got to get those rocks back. Like we've got to bring those back home. It's wild.
Okay, Bill Richardson, and then back to Tim for your other
Well,
question, Tim.
yes, on your last slide,
Mhm.
you started with B. Now is A because you think there's something there, or is A reserved for the sun?
Oh, I see. Yeah. So in the last slide I showed was in
Yep.
the Kepler system. When we're naming exoplanets, I don't know why this is just like the convention, but they always start with B in the system
All
and then
right.
move out from there. Hmm.
So I was hoping maybe there was something else there you don't quite have yet.
And that's what I thought too the first time I was like learning about exoplanets. Now they just by convention start with B.
Okay, thank you.
Tim, what else did you?
Oh, I've got a list.
Well, go ahead.
Okay.
Uh, first of all, how did it take a selfie that appears to include the image of the camera? Because I can understand stitching together a bunch of, images as you rotate the camera, click, click, click.
This is a great
What?
question. So the rover has this giant arm on it. And at the end of the arm is a camera. So what this thing did was the arm rotated around, took a bunch of pictures of itself, and then they basically did some processing to remove the arm out of the image. So there's a whole separate
Oh,
camera outside. Exactly. It's really challenging to get a selfie of these things, which is why they don't do it very often. It takes a lot of processing and kind of indicates the importance of that moment, right? If you ever see a moment where a rover's taking a selfie, it's usually because it was such an important moment that they wanted to do the whole thing. But there's some really good videos online that actually show you how they take the image and then process the whole thing together.
okay. That's going to be the next cool little feature for Apple to build into the iPhone to process the image to remove your arm.
That's so smart. They should do
Ah,
that, honestly.
ah.
Aaron, get on it. Oh,
There we go.
no, we
Uh,
can actually, we've been tutored, Sarah, to use the apple.com/feedback often and well.
Mhm. No, I mean that kind of feedback is useful. I worked in social media for like 2 years, and people usually only comment when they're mad about things. So if you can give positive feedback to people about like features you'd actually like to see or things they're doing well, I know it makes the teams behind the scenes very happy.
Tim, what was you wanted to get a copy of that?
yeah, just the website of that particular picture of Europa and its shadow on the Jupiter cloud tops. That's going to be my next desktop.
Totally, I can find that for you.
Okay. Yeah.
While you're looking,
Anybody else? I don't want to monopolize these questions.
yeah, Joe is next. While Sarah's looking for that, Joe, why don't you go ahead?
Yeah, this has been fascinating. Thank you very much. But I have a kind of a oddball question, which is closer to home. Reading yesterday about the garbage belt that got created by the Chinese rocket blowing up. You undoubtedly pay attention to that. If we don't start figuring out how to scoop all that stuff up, we're going to have a disaster of some sort, either with somebody in a Earth orbit like the space station or some rocket going up there. What's the potential solution for all of that?
It's a really good question. We've had several issues in the last months where things get exploded or crash or ripped apart in orbit, and then all the people in the space station have to hide for a little while, that kind of thing. Um, these objects just kind of naturally over time tend to fall towards Earth. So unless they're over a certain size, we don't have to worry too much. Eventually, they'll burn up in the atmosphere. But we're at the point where we actually have to start thinking about ways of removing things out or creating laws that mandate that at the end of a satellite's life, as an example, it deorbits. Because after a certain point, you reach this limit at which it becomes like extremely dangerous to even leave the planet at all. So NASA and the European Space Agency, and I believe some other space agencies, are actually working on these. They're kind of like satellite grappling devices. They've used spears or giant nets to capture objects and fling them in toward the Earth so they can burn up. Um, but I mean, the truest answer is that we really need to start like creating international treaties around this, especially as we send up larger satellite constellations. Like if we think about SpaceX's Starlink satellites as an example, the first time that they got their approval from the FAA, I think it was something like 20,000 satellites were approved. And then shortly after that, Amazon asked for approval for their own satellite constellation. And it's, as more and more companies create their own satellites or their own satellite constellations with tens of thousands of satellites in them, it's going to become even more necessary for us to regulate on this. We also need to create better systems of tracking these objects, which I believe is part of why the Space Force was kind of, created. We need all of these objects in a more real-time manner to be tracked so we can know whether or not they're going to be crashing into other objects, especially when we're dealing with other space agencies as well. There have already been moments where the European Space Agency has to divert their satellites because a SpaceX satellite was in the way and the data wasn't up to date and they couldn't communicate well enough to figure out whether or not they needed to move it. So they just cut the lifetime short on their satellite and moved it anyway, just in case, right? And this is just the beginning. You know, we really need to start worrying about this, especially if we're going to be sending humans up in a broader capacity. But thankfully, you know, a lot of people do think about this and do try to deorbit their stuff. As an example, when the Planetary Society sent up our space mission, Light Sail 2, it's deorbited and it's gone now. So ethical space missions.
What effect on the atmosphere is being created by burning all this stuff up at the top of the heavy atmosphere? I mean, it's a lot of stuff that we've shot up there and let it fall back and burn up. Is that at all an issue?
At this point, not so much, right? Things fall into the Earth's atmosphere from space all the time. Meteorites and things like that burn up. They're all very heavy in metals and that kind of thing. If we do it enough, if you know, fast forward several hundred years and we're burning things up in the atmosphere all the time, I'm sure we'll have to do some serious studies on this. But at this point, it's kind of like a drop in the bucket. I don't think we have to be super concerned.
Speaking of concerned, what about the three-body problem?
The actual problem or the books or the
books.
TV show too.
Well, I haven't seen the TV show, but the book.
Yeah. No, I've only read because I watched the first season of the show, which recently came out, and I'm in the middle of book 2. So I'm not all the way through to the ending yet, but I love this. I love this idea. So for people who aren't familiar, the idea behind the three-body problem as a book concept is that there is a species that lives on a world that is orbiting a ternary star system. They have 3 stars. And so their planet isn't in a stable situation, right? It's either too hot or too cold, or you know, like things are constantly changing, but life still manages to exist on this world, right? And it gets complicated. I'm not going to spoil the rest of the book series, but like this is a great example. Like we're looking for worlds that we think are going to be, you know, really stable and very Earth-like, right? But who knows what the limitations are on how robust life can be and what it can survive, right? Which is why I personally, like, I'm really invested in trying to find life on the moons in our solar system, because I think if we find them in these extreme situations where they're under the ice or something like that, that's one more data point that suggests that like life, just like life on Earth, isn't necessarily the rule, right? Who knows? Maybe there's life all over the place and we just don't know because it's all bacterial and we just haven't detected it yet.
You know,
Thank you.
what I was going to say is, you know that we're at a place that isn't sustainable about the low Earth orbit problem. You know, when I read about Amazon wanting to do this, I cringed.
Yeah, I mean it's really interesting because these systems are doing something that's very powerful for humanity. Being able to offer satellite internet to everyone on Earth, even if they live in remote locations or if they're underprivileged, like this could be game changing for people all over the planet. That said, we can't have tens of thousands of satellites all crashing into each other and creating a layer of debris around our planet that prevents us from leaving. Like, you know, we're not at that point yet, but we are at the point where we really need to start thinking about it. Because if you look at the videos, there are people who have done visualizations of the amount of space debris we have just orbiting our planet at this point. It is kind of absolutely startling.
Well,
You know what?
The
When
Chinese
you when
the
you think
Chinese are
about
putting
it,
their own constellation up there. That's what that
Yep.
Long March explosion was, where they want to, and it's worth reading the recent David Ignatius book too. But they want their own constellation that is, well, it'll have to be bigger from their perspective than all of what Musk is putting up there and Bezos and everybody else.
Yeah. And you know, who are we to say that they can't, right? There's kind of like one major treaty that kind of governs the way that different nations deal with each other in space, the Outer Space Treaty. It was from 1967. And at the time, they did not anticipate that we were going to be able to produce this number of satellites, or that corporate entities were going to be able to go out into outer space, right? Like, say that there are laws saying that a government cannot claim another world, but there's nothing saying that a corporation can't, right? There's a lot of complexities here. There's rules in there saying that you can't send nuclear weapons into space. But what happens if an asteroid's coming our way and the only thing that could save us is nuking that thing? There's law against it, right? So we need to. I'm personally think we need to find new ways to update the Outer Space Treaty and incorporate things like that. Because man, we're going to be in for a bad time if everybody creates their own satellite constellations and they're not communicating with each other about it. That's going to get wild.
But aren't things at least more promising about heading off asteroids with the mission? What was that? A nudging
DART,
mission?
yeah, the double asteroid redirection test. It was my first launch ever. I went to go see that thing go up from Vandenberg Space Force Base, and it basically, so there's an asteroid that had an asteroid moonlet. Didymus was the main one in the Dimorphos. Is this little moon that it crashed into. We hit that thing so freaking hard that we changed its shape, we changed its orbit, we changed everything. But it was our first planetary defense test of its kind. But like this is the beginning of the testing, and I know China is already working on their own version of this kind of mission. But I mean, this is one of those situations where you've got to be able to see it way out. If the further away it is, the further you detect it, the smaller a nudge you need to give it in order to get it out of the way. But there are also different kinds of asteroids, is what we're figuring out. They're not just like these chonky rocks, but also these rubble pile asteroids that are basically like ball pits of space rocks that just fly apart and then can reform over time. So there's like a lot that we need to figure out how to do that. But the fact that we're actually doing planetary defense missions at this point, finally, is it's a great step forward.
Tim, more from you. Go ahead.
Oh, you're muted.
Okay. Gravitational microlensing. Can any satellites do this for planets? I understand it requires much more precision than simply transit data.
Absolutely. Yeah. So microlensing, essentially, when you're trying to look for worlds, is when you wait for like a really big object on one side. Uh, how do I explain this in a way that's like succinct? So gravitational objects bend space-time essentially. So if something's really, really massive, you can actually get the light of objects that are behind it bent all the way around this object, and sometimes it amplifies it, right? So you can actually use large gravitational objects to amplify the light of a star system and actually brighten the planets that are behind that like larger chunk of matter. Um, we do have the technology to do this, and we have done it before with satellites. But I don't think there are any like dedicated missions that just specifically do microlensing. I could be wrong. Um, the interesting thing about that is that it really allows you to see like these smaller objects or ones that are way more distant, but because they're more distant, they're less of a target for our analysis of their atmospheres, because that would be even more challenging. We're really trying to focus on trying to find habitable worlds that are close in, because then we can like really, really analyze their atmospheres.
Okay, so most useful for more distant objects, requires repeated observations. Uh, so
Yeah.
comb through all of the public data where Hubble looked at the same thing 400 times and
Yep.
look at the stuff they were not looking at off to the side to look for microlensing.
Exactly. That's basically it's basically how people do that. And
Okay,
thankfully we have
same
a wild amount of data at this point. So, this is a rife place for future research.
petabytes of free
Yeah.
public data. Uh, So next question, same topic. How about using relativistic precession to detect the masses from transit data? Because right now transit data is not good for masses, but if you do
Correct.
relativistic precession with enough accuracy, such as the precession of Mercury around the sun that
Mhm.
basically proved Einstein's theorem yet again.
Again.
So
But
maybe
yeah,
you could
no,
maybe you could translate that to us, Sarah.
yeah. So essentially when, gosh, How do I even? How do I even? It's like I feel like I need diagrams in order to try to explain it.
Well, we have a whiteboard. You want to whiteboard it?
Now here, let me see if I can find a graphic on our website.
Yeah. While she's looking, the basic concept of precession is that if you have a planet orbiting in an ellipse, the ellipse doesn't just stay in the same orientation. The axis of the ellipse slowly drifts around the sun, in the case of Mercury, so that it's the high point of the orbit is slowly drifting across the field of view. And that's just basic Newtonian mechanics. But astronomers noticed 100 years ago that, wait a minute, the precession of Mercury is not following Newton's laws. It's violating them. WTF.
Yeah,
Then
I can't find it.
when Einstein invented relativity, discovered relativity, that explained it. And using Einstein's equations, corrected the small error that Newton's equations couldn't account for.
I mean, once more, right? Like Newton's equations are kind of like a simplified version, essentially. I couldn't find it on our website, but I did on Wikipedia find something that visually shows what you're trying to explain. So, like anything that goes around in an orbit goes around in that ellipse, and the angle of this ellipse is basically kind of rotating, which, if you're going to be looking at a world going around another star, could impact the timing of how it's going around.
Exactly.
Essentially, you would have
Exactly.
to do many repeated observations of this. If the planet was closer to the star, its orbit is going to take less time, so you would have a better chance of being able to figure that out. Which is okay. We found many objects close in toward their stars, even like Jupiter-sized objects. I'm sure people have tried to do this. Um,
TRAPPIST
yeah.
1.
Have they tried to do that for TRAPPIST-1 with the masses?
It's just an incredibly rich data set, and the amount of attention it's receiving is
Hmm.
causing it to have a lot of data collected. So
It's true. Although I'm guessing, and this is just a guess, but I don't know how much precession would be in the system, given that they're in this kind of what is the word for it? Because all of the planets are impacting each other's orbits in such a way that they're kind of going around in these like synchronous orbits relative to one another, it might have less option for the actual precession because their orbits are being shaped by each other, right? If it was one giant star that was impacting this precession, it'd probably be more of a dramatic impact. But with so many objects in the system, it might be a less pronounced effect.
good
I
point. The three-body data problem is going to swamp any small change in the precession. You need a single object orbiting a star.
Exactly. But for single planets, that's probably a really good way to do it. Given that, it is really difficult to tell the mass of an object because you're kind of you can see how much of the light it's blocking out, but you don't know whether or not that thing is just like really, really big and close up or really, really far away. Like trying to gauge its mass. You could try to tell that, you could try to figure it out by how long it takes to go around the star and how much light it blocks out. But with all these things combined, you'd have a much better understanding. Oh, and I see your last question is, what is the name of your cat? My cat's name is Ada. She was named for a character in the video game Destiny 2, which is a game where you explore the solar system. But I believe that character's name, although I haven't heard this from their actual mouths, but I read online that it could be a reference to Ada Lovelace, who was first programmer, depending how you define it.
Video game developers, that's highly likely.
Highly likely.
Do you know, with in our Zoom meetings, we're disappointed if the cats don't make an appearance in the meeting.
Is she out here with me? She is. She's actually in this chair right here, taking a little nap.
Yep.
She's actually a rescue cat. She was given to me by someone who found her, and they brought her a picture up to the observatory where I was working, and the rest is history. Took her home.
So, Sarah, what was your recent NASA thing that was also occupying your time this week?
Oh yeah, so in a few weeks, I'm going to be hosting the webcast for NASA's Innovative Advanced Concept Symposium, or the NIAC program is the program it falls under. NIAC is, excuse me, it's one of my favorite parts of NASA because it's the thing that funds the really innovative, really strange, very like conceptual things that might happen. Not all of these programs all make it to the end, right? But this is the program where they think of things like mobile pharmacies for going to space, or nuclear probes that can melt beneath the ice sheets to actually get down into the ocean. Or my favorite from last year was this, it's an airplane that flies around Saturn's moon Titan and lands in the seas, and like gets samples out of the atmosphere through capillary action in the wings. Like this is some wacky, really out there stuff, but at the same time, like really foundational. If we end up building planets on, or building housing on other worlds using like mycelial spores and like mushrooms and stuff, it's going to be because of that program. So I'm going to be there in, I think it's September 10th through the 12th. It's in Pasadena, California, and it's free, but the whole thing is webcast online, as a lot of other NASA conferences are.
Well, maybe if you can send us a link to that for the
Yeah.
people who are interested. And it strikes me that we're in a really good kind of time and place for that sort of innovation where it can be translated through commercial means, not only publicly paid means.
Yeah, that's what's really cool. There are like several private companies that show up to these events with their cool ideas that they've proposed to NASA and get some of that seed funding for the technologies. We also do a grant program at the Planetary Society called the STEP Grant Program, called Science and Technology Empowered by the Public, where we have people write in their cool ideas, and we pick a few every couple of years to help fund. We've done one for techno signatures. We recently did one related to food and space. Um, it was also it kind of came out of our program for light sail, because we wanted to create a solar sail, mostly because Carl Sagan and Lou Friedman, our founders, were really into it. But we managed to fully crowdfund the spacecraft with contributions from 50,000 people from all over the world. And so that kind of sparked our want to create a more robust system for kickstarting these other cool projects.
Oh, so I think I was also going to ask, do you think there's going to be any kind of follow-on to the solar sails missions? Those were really cool.
Yeah, well, so we collaborated with NASA. We gave them all of our data, and they started working on some other missions. The first one was Nia Scout, which they launched into space, but unfortunately, because of the rocket that it was on, the rocket had some issues and was on the tarmac in Florida for a little too long. And my understanding is that the batteries on the Nia Scout didn't work, essentially. So this mission didn't go forward. But recently, the second solar sail mission that NASA was working on, the ACS-3 mission, launched, and we're supposed to get more information, gosh, in a week or two about how its deployment went. So we got that mission up there, and then of course Japan and the JAXA program created their Icaros mission, which was the first solar sail that actually worked, and that one totally worked as well. So more and more people are beginning to start using this technology. And I think there's an upcoming solar mission they were planning on as well. But the one challenging bit there is that the solar sails are only effective for kind of small spacecraft. So you could send CubeSats and smaller instruments into space, but getting an entire, like trying to power up a whole ship and send that somewhere with it would be excessively challenging. But the reason people are excited about this technology is because you can basically propel something without any propellant. You just use light bouncing off of the solar sail in order to propel it somewhere. And we could extend that to things like lasers, say, and then shoot very small small spacecraft out beyond our solar system and maybe even to other star systems. So I think chances are, if we're ever going to get ourselves out to, Proxima Centauri or other star systems that are nearby, it's probably going to be solar sail first, is going to be my guess.
So the idea of it is that once you're way, way out deep in the solar system, the propellant effect is not going to be as great, but the speed will have accelerated the craft, right?
Yeah, so at that point, you've already accelerated up to a high velocity. You might not increase your speed over time, but you've already hit that speed and it's going to stay consistently with that speed. It might be slowed down by interstellar dust and things like that on the way, but that effect won't be that pronounced compared to how fast you get it going, depending how fast you get it going, right? But you could hypothetically charge one of these things up to, sublight speeds, get it going really, really fast, and then we wouldn't have to worry quite so much. You might have to build it out of a ripstop material or something so that a tiny micrometeorite doesn't blow the whole thing apart. But, you know.
Sarah, this has been wonderful. Pi members, any other questions for Sarah? Yeah, so we will repose your talk on YouTube, and I'll send you a link to it, afterward.
Thank you so much.
The other thing is share Pi mug. So
wonderful.
we would like to send you a handsome Pi mug in appreciation for your talk to our group today.
Thank you so much.
So you will, the only thing we'll need from you is, at some point, is a snail mail address.
Totally. And it's funny, I believe my colleague Kate Howells gave a talk to your group in the past, and I think she still has that mug. I think I've seen it.
Yeah, Kate was terrific, and I think that's what gave us an appetite to, uh, um, to have another space program. And your present has just been fabulous, just fabulous.
Thank you so much.
Thank you so much.
And if you guys are interested, if you liked Kate Howell's talk, she just came out with a new book about the moons of the solar system. It goes over a lot of the stuff with Enceladus and Europa, but with amazing, beautiful images from all the most recent spacecraft. I highly recommend it.
Oh, well, include a link to that.
Let's see if I can. Oh, I'll have to write her to get the link, I think, because it only just came out.
Well, send it to me and I'll
I can email it to
in
you.
the recap for the meeting.
Awesome. Well, thanks so much for having me, everyone. And if you guys have any questions about anything like this, please feel free to email me. It's radio@planetary.org or planetaryradio@planetary.org. And if you have any questions, I'm happy to figure them out. If I don't know them, I can contact all the scientists that work on these missions. And I frequently like to get people's questions that they ask me in the email into our podcast. So I'll go out of my way to figure out what those answers are for you.
Well,
Thanks very much.
if you could put in whatever contact information that you'd like us to send around, sure.
Type this into the chat. Perfect.
Now you're in the Bay Area, aren't you?
I'm in the LA area. We're in Pasadena, right near the Jet Propulsion Lab in Caltech.
Mm-hmm.
Yeah, we've got a really cool headquarters. It used to be a bank, but we've repurposed the bank. We've got some really wonderful artifacts from science fiction and science history, some really cool things from Carl Sagan in there, and some beautiful scale planets in on the roof. I frequently find Bill Nye screwing new meteorites and things into the walls. So if you're ever in the area, we're not open for tours since COVID, but for special requests, we can get people in to check things out. One of the things I really love is if anybody's a fan of Star Trek, the original first Star Trek movie, there's a scene where they're flying by Jupiter. We have that original Jupiter globe in our office.
Well, Pi members, keep this in mind that if you have occasion to visit LA, to take advantage of this wonderful, wonderful offer.
And there's many places if you are in the LA area to go check some things out. The Jet Propulsion Laboratory has a beautiful area that you can go to by the Von Karman Lecture Hall that's open for some beautiful stuff. SpaceX has their Falcon 9 rocket right outside of their building. You can't really get into the building without a special pass. I've been in there before, and it's wild, but the rocket is really spectacular. And then the Space Shuttle Endeavour is actually at the California Science Center, really nearby as well. So if you ever want to take a space tour, the LA area is a really good place to be. Although Florida also highly recommend.
Well, in our area on the East Coast, we're limited to Wallops pretty much.
Yep.
Hey, Jonathan, how about hybrid meetings?
Oh, from LA, you mean?
Yeah.
Well,
Take a camera around, live stream it.
yeah, we're trying to get better at actual hybrid things. Because many Pi members, we lost a lot of people during the pandemic. At the same time, as I mentioned right at the beginning, we also have gained a lot of people who used to be local and now live far away. So the challenge is to make a meeting as meaningful for the people who are there as for the remote people. And that's not so easy to do.
And strangely, because we used to have most people in the office, but we do have some people that work with us internationally that would be in on our virtual calls. Now that almost all of our meetings are online, it actually has kind of increased our interactivity with everyone across the board because it makes those meetings feel like a lot more equal, right? And then we try to get everyone together. We get our entire Planetary Society crew together maybe like once or twice a year at the office. And I tell you, it's, after being in this COVID era where we're all on Zoom calls or Google Meets together, being able to see everyone face to face is next level. And we're very lucky because we work in a field where, we're very passionate. We just talk about cool space stuff all the time. So whenever we all get together, you can imagine it's a ridiculous space party at all times.
All right, then. Well, thanks again so much, Sarah. And so I'll send you the link to the YouTube. And if you send us a snail mail address, we'll send you a pie mug. Yeah, so, well, you didn't have to get up too early, but thanks
Oh
for
no, I
getting
mean,
up.
7 a.m. ain't bad. No worries. Thanks so much for having me. And if you guys have any space questions, let me know.
Okay.
All right. Talk to you guys later.
All right, then. Did everybody who wanted to sign in to the Pi Attend where we'll do the door prize for the meeting? Oh, Mary, I think Roy was going to send you the AirTag from your door prize from the last meeting.
He did. Thank you very much. I'm happy.
Terrific, terrific. Thanks, Roy. Okay, well, let's generate a winner for today's meeting. And the winner of the door prize today is Jean Haddon. Jean, are you still here? Yeah, so congrats, Jean. Let us know if you would like an AirTag or a Apple gift card as the door prize for the meeting today. You have to unmute, Jean.
I've never had an AirTag.
Well, are you ready to have
Yes.
an AirTag that adds to your Find My?
Um, that's exciting. I'll have to get back to you and find out how the current way of using them. And I left you a message on the sign in also. I have a son who's going back to working at NASA and all the space stuff, and I want to be able to send him a recording of this very interesting meeting.
Gene, the recap that we'll send about the meeting will have the YouTube link for the live
Great.
stream, which I'll now turn off. So thanks to the YouTube audience for watching today.